Okay, just real quick, we're rocking and rolling on things. I just wanted to make sure, though, that everybody was aware that 2 weeks from now we have our first celebration. We will be having an exam on Friday, September 23rd. Now, a little bit on the logistics of the homeworks related to that. So I put a little screen capture from the syllabus so that everybody kind of understood. So we're in lecture 8 right now. We're going to be continuing our discussion of truss analysis, and so we're going to be doing that today, Monday, and Wednesday. And so we have homework 3.2 assigned today, homework 3.3, and then homework 3.4. I'll go ahead and tell you lecture 11 is a little different. It will be, like what we're going to be covering is going to be, it's going to be very different from what we've been talking about up until now. But basically, this lecture 11 is where we discuss the basis by which we compute deflections in structures. And so we'll be talking about energy methods and things like that. So it's going to be a little different. I'm going to give you a homework on this lecture, but it is not going to be due Monday. It's going to be due that following Wednesday. So that one homework is going to extend 2 lectures. But the homework is going to be due Wednesday. That's homework 4. Because that's an exam review day, what I'm going to do is the moment that it's due, I'm posting the solution. So you'll have the homework solution for studying for the exam, but the downside is I'm not going to accept any late homework on that one assignment. Okay? Does that make sense? All right. So yeah, so you'll have 3.2, 3.3, 3.4, homework 4, and then we celebrate. Okay. All right. So let me escape out of this. Close this. I don't know why this is showing up. Is this lecture? Okay. I don't know why I was doing that. Okay. All right. So what we're going to be doing now is continuing our discussion of trusses. I want to take a step off to the side, though, and talk a little bit about the stability and determinacy of trusses, because we haven't talked about that yet, and it's, I don't want to say a little different, but there are some things regarding the internal stability of trusses that need to be observed, and we'll talk about that in a bit. So, let's recall from the previous lecture. So, our assumptions. So, the 3 assumptions that we make when we analyze a truss are that we assume that all of the members are connected by frictionless joints. We assume that all of the loads and the support reactions are applied at the joints. And at each joint, we assume that the centroids of each member coincide. And so what that means is that when we analyze a truss, we can sufficiently assume that all of the members are carrying only axial loads. So no shears, no bending moments. So that's why when we look at the method of joints and we look at each member, we're only drawing either axial loads in tension or axial loads in compression. Because the 3 assumptions that I previously stated have baked into them the inherent idea that there's no shears and moments. So, we have 2 methods for analyzing a truss, the method of joints and the method of sections. How did homework 3.1 go? Was that pretty straightforward? Anybody have any questions? Good deal. So, if you understood homework 3.1, I think homework 3.2 will naturally be pretty straightforward. We're going to do method of sections later, but I want to take a little bit of a tangent and talk about internal indeterminacy. So, if you recall, we express indeterminacy through a quantity that we termed I. So the last time that we dealt with indeterminacy, we called it I sub E, because that was the external indeterminacy of a structure. And what we were doing was we were comparing the knowns versus the unknowns in a truss analysis. And we found certain patterns with I. So for instance, if I was negative, the structure was unstable. If I was 0, the structure was probably determinate. And if we found that I was positive, it was probably indeterminate. When I say probably, the probably is about the aspect of stability. So if I is 0, it is probably stable and statically determinate. If I is 2, it is probably stable and statically indeterminate to the 2nd degree. So let's talk about what that means. So again, here's our degree of external indeterminacy. And the way that we computed that is we took the number of knowns and the number of unknowns and compared them. And so this formula here, I I equals R minus EC plus 3, this is essentially the unknown quantities minus the known quantities. So the known quantities are 3 plus EC, and why 3? Because at a structural level, we have 3 equations of equilibrium that we know. We know the sum of forces in the x direction is 0, sum of forces in the y direction is 0, and sum of moments. So I'm curious, do you think I'm going to be using 3 when I'm looking at trusses? You're shaking your head no. What number am I going to use? 2. 2. Okay, that's a good point. So with joints, there's only 2 equations of equilibrium per joint. So maybe we'll see the number 2 pop up in the IT expression. Spoiler alert, we will. Now the number of unknowns is the number of support reactions. So we said that if IE is negative, the structure is unstable, just period. If it's 0, it should be statically determinate, and if it's positive, it should be statically indeterminate. And by the should be's, we're talking about, remember, the reactions can't all be concurrent, can't be dealing with like a wheel type scenario, and the reactions can't all be parallel like a skateboard. So, okay, let's talk about internal indeterminacy. So we're going to apply the same logic, the same idea, but I want to look at it from a truss perspective as opposed to an overall structural perspective. So I want to look at this truss. Regardless of the loads, can I compute the support reactions on this truss? I say yes, okay? And I say yes because if I, let's see, I hope my pen will work here. I think it will. I have a reaction here, a reaction here, and a reaction here. So 3 equations, 3 unknowns. If I'm just looking at the support reactions, can I compute the support reactions on that truss? You bet. There's no reason I can't compute those support reactions. But now let's start looking at it from a method of joints perspective. When I do a method of joints analysis, I have to start with the joint that has how many members? 2, right? Because I only have 2 equations of unknown, or 2 equations of equilibrium per joint. So how many unknowns does this joint have? 3. This one has 5, 5, 5, 5, 5, 5, 3, 3. Damn, that's a problem, isn't it? That's a problem. We cannot solve this truss using only the equations of static equilibrium. This truss is internally indeterminate. There's too many unknowns inside the structure in order to solve it using just the equations of equilibrium. Okay? And so that leads to a comparison, another comparison of knowns versus unknowns. So if we look internally inside the structure and we ask how many known quantities there are, I propose that there are 2 known quantities for every joint. Those are the equations of equilibrium. I know that at every joint the sum of forces in the x direction is 0 and the sum of forces in the y direction is 0. The unknowns, well, what are the unknowns? There is 1 unknown for every member, right? What's the unknown force inside this member, this member, this member, this member, this member? So there's an unknown member for every, or an unknown quantity for every member. There's also the unknown support reactions. So I can take the number of unknowns and the number of knowns and develop this. This is the degree of internal indeterminacy in trusses. M plus R minus 2J. It's in the same fashion as the previous expression, the unknowns minus the knowns. So what are the unknowns? The unknowns are M plus R. M plus R. M is the total number of members. R is the total number of unknown support reactions. And I use that in this expression because on the joints, we do have reactions applied to the joints as forces. So they do qualify in this expression as well. And as for the number of known quantities, I have 2 known quantities per joint. So M plus R minus 2J. That's the I sub T term I mentioned earlier, the degree of internal indeterminacy. Now, if IT is less than 0, the truss is internally unstable. Okay? This, I believe, is an example of a structure that is internally unstable. Look at this structure right here. So M plus R. I have 3 reactions. 1, 2, 3, 4 members. M plus R is 7. 4 joints. 1, 2, 3, 4. 2 times 4 is 8. So I sub t for this structure is -1. That structure is internally unstable. It's internally unstable because you could apply a lateral load and the structure would just collapse. But it's also internally unstable because the I sub t term is negative. So, if I sub t is negative, the structure is internally unstable. If I sub t is equal to 0, the truss should be internally stable and statically determinate. If it is greater than 0, the truss should be internally statically indeterminate. And I say the note on should be, so here are the 2 rules for whether or not a truss is internally stable. So first off, it's got to be externally stable. So all the rules before about the reactions can't all be concurrent, the reactions can't all be parallel, that's got to hold true. If a truss isn't externally stable, it's not going to be internally stable. Now this next bullet point is admittedly kind of hard to understand, but it is the rule. The rule states that the truss must be constrained against rigid body movements. In other words, if it's not constrained against rigid body movements, something like this would happen. Now, if you want to know how in the heck do I look at a truss and determine whether or not that's true, a clear indicator of instability is if you have a region in the truss where there's no triangles. Okay? This is an example of a region where it's just a square or a rectangle. This is a region that's internally unstable because there's no triangles. If you have a truss that doesn't have any triangles, chances are it's unstable. But we don't really build a lot of those types of trusses in the real world anyways. But that's kind of what that bullet means. I know that bullet's maybe a little tough to understand visually, but that's kind of what it means. Any questions? How's another example sound? Let's do another example. So I want to do this example. This example is a little bit more intricate from a slope ratio standpoint. Because if you look, I've got oodles and oodles of diagonal members, and I've got different slope ratios for each member. So I have to be much more cognizant of what I'm doing from a bookkeeping standpoint. Okay, so that's point 1. Point 2 is what I got going up here in the top right corner. If you go through and count the number of members in this truss, you will get 21 members. Okay? Now how do I get that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, and then 1 is in the one in the middle. So there's 21 members in the truss. There are 3 reactions, 12 joints. 21 plus 3 minus 2 times 12 is 0. So the truss is stable and statically determinate, both externally and internally. So this is the type of truss we're going to be dealing with. On your class analysis project that we do later on in the semester, one of the requirements for the truss that you lay out is it must have an IE and an IT value of 0. So it will be externally and internally stable and statically determined. So, okay, now I've given you the support reactions like I gave you last time, but there's something else I've done with this truss that happens a lot in the real world. What happened with this truss that didn't happen in the last one? What is this truss exhibiting? It's symmetric. In other words, I have the same loads on this side as I do on this side. And not only do I have the same loads on one side that I do on the other, I have the same geometry on one side than I do on the other. That happens a lot in the real world because we as engineers engineer trusses that way. I would prefer trusses be symmetric whenever possible. Okay? Keep it simple. But why? What's the benefit? Well, what's the benefit from an analysis perspective? Well, what is the force inside member AB? It's whatever the force inside this member is. Member BC, whatever the force inside member BC is the same thing as in member EF. In other words, because the truss is symmetric, I only have to solve half of it. And whatever is on the other half is mirrored. Okay? Now, I want to be crystal clear. This only works if both the geometry is symmetric and the loading is symmetric. If I were to take this 6 kips at L off, if I were just to erase that, suddenly I have to analyze the whole truss. Okay? It's only when both the loading and the geometry are symmetric. Something that will also happen in your class analysis project. We will have a symmetric structure. So, you should have a symmetric structure. So, it will be up to you how to lay it out, but I would do that. Okay. All right. So here's my structure. Notice that I've given you the support reactions, and I think they're much more easy to see this time because I've got 6, 12, I got 30 kips going down, so I got to have 15 kips going up, so it's 15 kips at each support. So I think that part's pretty easy. Okay? So, like last time, and we sort of figured this out afterwards, I kind of want to do this now. What I want to do now is I want to develop our game plan. In other words, the order in which that we're going to solve this truss. So let's do that. So which joint do you want to solve first? So we'll say we'll call this order of solution. Which joint do you want to solve first? Everybody's quiet. Well, can I solve joint I first? Why? There's too many unknowns. So it seems like I'm going to start where? A. Right? So I'm going to solve joint A first. And joint A is going to give me this member and this member. So what's the next joint I'm going to solve after that? H. H is going to give me this member and that member. Okay, so now what? B. Okay, and B is going to give me that member and that member. Then what? I. That's going to give me that member and that member. So what's left? C. C. And now hold on. Got C. And then I'm going to have one member left in the middle. I could solve joint J and get that member, but I'm lazy, so I'm going to solve joint D and get that member. Now, why am I saying there's only one member left for joint D? Because if I know this member, I know this one. They're the same because the truss is symmetric. Make sense? So now we know the order of the solution. We know our game plan. We just kind of need to rock and roll this thing. But I got one more thing I want to figure out. Okay? I want to figure out some of these. We should look at some of these slope ratios, huh? What's the slope ratio of these diagonal members right here? So, like this GL, or in this case, this AH. We go over 12 and up what? Do y'all understand what I mean by this notation right here? So this means that the total length is 72 feet, but from here to here is 12, 12, 12, 12, 12, 12. So what's the slope ratio on this one? 1 to 2. Okay. What about this one? What's the slope ratio on that one? 1 to 1. What about this one? So we go up 18, go over 12. So, is that right? 3 to 2? Okay, so now we've got different slope ratios. So what this means is that we really need to be cognizant of what order we solve these in. Okay, I'm going to write this order in H, B, C. I'm going to write that order just so I have. Okay. All right. So we agreed we're going to do joint A first. Here, let me scroll up a little bit so we still have the joint in view. Okay. So we've got the joint. We have a member. Bless you. A member. We have a load up of 15 kips. Then we have this, which we'll call A, B. And then this is 1 to 2, right? So we got to be very cognizant of incorporating the correct slope ratio on the correct member on this truss. Okay. So you tell me what to do. I'm lazy. I want you all to tell me what to do for a change.
Same forces the Y.
There we go. What does that tell me?
I'll give you AHY, the Y dependent AH.
Okay, and what is it?
15 kips going down.
Okay, so that means this goes down. All right, somebody else. Mr. Mount's doing enough work. So, all right, so that's correct. So now what do I do? Somebody else.
Then you use slope ratio to find X.
There we go. So slope ratio. So AHX. And how am I going to do that? So it's going to be AHY times something. What goes in here? Some fraction. Huh?
2 over 1.
No, it's not 1/2. It's 2 over 1 because I'm solving for the horizontal component, and the horizontal component's got to be bigger, right? So basically, because it's AHY is to 1, as AHX is to 2. So we're going to be doubling that, and this is going to be 30 kips. Now, help me out. What direction do I draw that arrow? To the left. All right. So now what do I do?
Some forces in the X to get AB.
And what is AB? What direction? So that means that goes like this. That goes like that. So, anything left I need to do to summarize this and move on?
Do you want to find the resultant?
There we go.
AH.
And so I do that doing what?
The square root of the square
There you go.
for addition.
This one I think is going to require a Casio FX 115 ES Plus or similar scientific calculator. I don't think this one's going to be as nice and pretty as a 345. The number of iPhone calculators is just...
I got 33.54.
Say again?
33.54.
Do I have a second on that?
Yes.
Yeah.
Okay. So, therefore, AB is experiencing 30 kips in tension or compression? No, AB.
Tension.
AH is 33.54 kips in tension or compression. That one's in compression. So. Isn't it so much better when you have your game plan figured out before you start even doing the problem. Like you know what order of joints you're going to do, what order you're going to solve the problem in. Here, I'll leave the A up and I'll say, okay, we've done that one. So next comes joint H, okay? Because again, we've got this member and this member solved, so that's joint H. Okay, so how many members do I have framing into joint H? I've got 4. So here's H. Okay, let's see. No, 3. I'm sorry, 3. Okay, so I have 6 kips. All right, I've got a known quantity here and a known quantity here. Because this is AHX, and that's 30 kips, and that's AHY, and that's 15 kips. AHX, do I draw this arrow to the left or to the right?
Towards the joint.
Towards the joint, which is to the right. And this one is, again, towards the joint. AH is in compression, so it's in compression here too. So we apply this like that and like that. So let's see. Now we've got our unknowns like that and like that and like that. So I'll call this unknown member BH. And I'll call this HIX, HIY. Okay. You tell me what to do. I've got my unknown. Oh, hold on. Wait. Let's make sure we have this clear. What's our slope ratio on that member?
2 to 1.
2 to 1. Okay. So tell me what to do.
So force X first.
X first, because I've got 2 unknowns in the vertical direction. I only have 1 unknown in the horizontal direction. Let's sum forces in the X first. So sum forces in the X direction. So how many known quantities do I have in the X direction? That's not the X direction. That's not the X direction. That's the only one, right? And that's 30 kips going that way. So what's the force this way?
Kips.
30 kips. So all right. So that means that arrow is going like that. So if I have HIX, what should your immediate reaction be? Slope ratio. I heard slope ratio. Go to HIY. So HIY equals HIX times something. And that something, I think we know, is either 2 over 1 or 1 over 2. Which is it? 1 over 2, because the y component is going to be smaller than the x component, and 1 over 2 is smaller than 2 over 1. So if that's 30, I know that's 15 kips, but what about the direction? Which direction is that going to have?
Down.
Down. So there we go. Now, I don't know about you, but as for BH, there's kind of a lot going on vertically. So maybe what we'll do is we'll be a little formal about it. We'll say, okay, let's sum forces in the y direction. Let's see what we get here. So I've got AHY is 15 kips going up. I've got HIY is 15 kips going down. I've got this 6 kips going down. So what's the only thing left is BH, right? So 15, 15, 6, and That's got to be 6, right? So BH has got to go over here, and that's got to go up. What do you think? Is that bad? That's straightforward? All right. So, last thing to do. But numerically, this is going to be the same as what we just did. And we're going to get 33.54. So, now help me out with these members. Are they in compression, tension? One's in compression, one's in tension. What's the deal? They're both of them in compression. That's 100% right. Because they're both pointing towards the joint. Now, I'll tell you that if, as you're going through this, there is a point that this is getting boring or getting same thing over and over again. Good. Because if you're getting bored, but you're able to do this easily, then you learn how to do it. And it's like I taught you something. It's kind of crazy, I know. All right. So now we're going to do joint B. Again, we're going to respect the strategy that we developed at the beginning of the problem. So we're going to do joint B next. So let's see what we got. And this truss is going to have something very interesting at the end. We're going to have an interesting result. You'll see what I mean. So let's draw out the joint. So the joint looks like this. Okay. What's the slope ratio on that diagonal? 1 to 1. So whatever the x component is, the y component is equal to that. Okay? Now we know this member, this is AB, and that is 30 kips. What about that vertical member? What's the deal with that vertical member? How much is in this vertical member?
60.
And going up or down? Down, because it's BH, right? And BH was in compression. I'll be honest, I think the hardest part about the method of joints is the bookkeeping. I think that's really honestly the hardest part, is just making sure that you keep track of, which direction things are going. I have seen students that what they will do is they will do these blown up joint analyses where they put like this joint here, and then they put, this joint here, And so if they get like an arrow that goes like this, then they put this arrow that goes like that. They just do the whole truss on this big, huge sheet of paper. And there's actually some logic to it because you can go through it pretty quickly. It just takes a lot more drawing. So, just a thought. So, for those of you that use some of those collaboration rooms on the third floor, you can just put the whole truss up. All right, so those are my unknowns, so let's name those. Let's call that BI and BI, X and Y, sorry. And then this one is BC. Okay. All right, so I think what I ought to do is some verticals first, and there's no loads applied to this joint. So we can sum forces in the y direction. And so BIY is going to be what? 6 kips, and that's got to go up, right? So the slope ratio tells us that because that's 1 to 1, BIX is BIY, which is 6 kips going this way. Now, if I sum forces in the x direction, what am I going to get for BC? $24. Going to the right. Because I've got 30 kips going to the left, 6 going to the right. I need another 24 going to the right. Okay. So the last thing to do, use my Pythagorean theorem. And then that is, that's 6 times the square root of 2. I don't think I can do that one in my head.
8.48.
8.48. Do I have a second?
Yeah.
And then, oh, I need to put my arrow on that. So therefore, BC is 24 kips in tension. And now they're both in tension. So I'm going to show you a little pattern. But before I do, I know I kind of went through this joint a little quicker than most. But does this make sense? Does anybody have any questions on this joint? Where are my markers at? Is this okay? So far, so good? Okay, I want to show you something. If you look at the truss in general, somebody help me out with the note keeping. AH, was that tension or compression? HI, was that tension or compression? Okay, AB, was that compression or tension? What about this one? BC. Tension. So it's funny, it's like all the members of the truss that are on the top are in compression, and all the ones that are in the bottom are in tension. It's almost like there's something to that. If I was a betting man, I bet you IJ is in compression. The reason why it's in compression is because I have a truss that's simply supported and all the loads are on the top applying downwards. So the way the truss is going to deform is sort of like it's kind of deforming like this. So the top is experiencing compression, the bottom is experiencing tension. The stuff in the middle will have a tendency to want to change signs depending upon the way the diagonals are going. So just food for thought. So we'll be able to talk more about those types of patterns later when we look at things like influence lines and whatnot. But just a random factoid for you. Okay, so we're going to do I. Okay, and I'm going to try and charge through I and C pretty quickly because I want to get to joint D. Joint D is kind of nifty. Okay, so joint I is kind of involved because joint I has, let's see, we've got diagonal members that go like this, but then we also have a diagonal member that goes like that, and a vertical member. And we got a 6 kip load. Woo! There is just all sorts of hullabaloo going on joint I. So we just got to make sure we're cognizant of our bookkeeping. So we have member HI. I think HI was 15 and 30. So this is HIX, which was 30 kips. HIY, which is 15 kips. We also have this member here, which is in tension, and this is, I think this was BI, so this is 6 and 6. Did I get that right? If I made a mistake, let me know. Marshall University policy says I'm allowed 7 mistakes per semester. But again, given the fact that I'm the one that keeps account of the mistakes, it is a corrupt system. I'm aware of that. So, that was a joke, not a very funny one. Okay, so I have a vertical member that's unknown, and I have this diagonal that's unknown. So we'll call this IJY, IJX, and we'll call this CI. Okay. So, looks like I should solve for the horizontals first, right? So if I've got 30 to the right, 6 to the left, I need another 24 to the left. So I think that IJX is to the left. Right? And so I think that the slope ratio tells me what's going on with IJY. What is IJY? Is it 48 or is it 12? Based on my slope ratio, is the vertical component going to be bigger than the horizontal or smaller than the horizontal? Exactly. So this is 1/2. And that's going to go down. So let's see. Maybe I can eyeball this. I got 12 down. 6 and 6 down, that's 24 down, 15 up. What do I need going up? 9. I think that vertical member is holding 9 kips up. So CI is 9 kips up. Do I have a second on that? You get the same thing I'm getting? Okay. So therefore, apply our Pythagorean theorem. If I'm going too fast, please tell me, because I know I'm kind of going through some of these joints kind of quickly. But I think they're kind of systematic at this point. So, again, I really want to get to this last joint, so it's kind of cool. Okay. So when you chug this out, I think you get, what is that, 26.83? So CI is 9 kips in compression. IJ is 26.83 kips in compression. Okay, I'm going to mark a line. Then I'm going to take a second, let everybody kind of catch up. We got 2 more. Truss analysis isn't hard. It's just, it can be a little tedious. Okay. Everybody good? All right, 2 more joints. And again, that last joint. Cool. So we said we're doing joint C. So let's look at joint C. So there's no loads applied to joint C. Goes like that, like that, and then there's a diagonal, and I think that diagonal was a 2 to 3. Was I right on that? Okay. CI is 9 kips. Again, I'm drawing it downward. I had it upward here, but it's applied towards the joint, applied towards the joint. So because it's in compression. And then we know this member right here, that's BC. What was BC? 24. And it was in tension, right? So yeah. Oh, by the way, didn't I say IJ would be in compression? By the way, y'all shoot, look at that. It's not like I had the problem done in advance or anything. Again, I'm a dork, I know. So, some forces in the Y, slope ratio, some forces in the X. So, we'll call this CJY. If I made a mistake, let me know. I will take it personally, but then I will fix it. Again, it's a joke. Alright. So we're going to sum forces in the Y direction. So what is CJY going to be? 9 kips going up. So if that's going up, that's going to the right. Now, is it 2/3 or is it 3/2? 2/3, which makes it 6 kips. Exactly right. You beat me to it. And then summing forces in the X direction. We have CD, so I have 24 going this way. I have 6 going that way, so I need another 18 going this way. Y'all are troopers on a Friday, especially if this is the only class you came for. Alright, so what do we got here?
10.82.
10.82.
Tension.
There we go. Okay. I think we're on our last joint. I think you're the only person that had that reaction. Get it? Reaction. Just, again, I'm a dad. Be ready for the dad jokes. They're going to be coming. Just, can't help it. Baked in. Okay. Joint D. Something's interesting going to happen at this joint. So here's the joint. That. Now, the only member that we know is this member right here, CD. We don't know this member, which we're going to call DJ. And we don't know this member right here, which we're going to call DE. Now, sum of forces in the x direction tells me that DE is 18 kips this way. But we kind of already knew that because symmetry told us that that was going to be the case. And you can continue the rest of the truss analysis and you'll find that the answers start mirroring one another. Like this diagonal matches this diagonal and this one matches this one, etc. But this DJ, this one's weird, okay? Because I have the sum of the forces in the y direction. What is DJ?
Zero.
It's 0. Huh. It's 0. It's not tension or compression. It's nothing. DJ is a 0 force member. Okay? The answer is 0. So DE is 18 kips in tension, and then DJ is 0. It actually is carrying no load.
My next question.
Yeah.
Why is it there?
Why is it there? There you go. It would be interesting if we had some of the lecture on Monday devoted solely to 0 force members. It's like I had a plan. Now, what clickbait for the YouTube video. No, so I'll give you a short answer. I'll give you a short answer that can relate to the math. Tell me, didn't mean to close that, but I can open that back up. What would happen to this if that member wasn't there? What would happen to this?
It would be unstable.
It would be unstable. So if we removed that member, the structure would be unstable. We would create a collapse mechanism in the structure. So that is one reason. But if I'm being honest, that's kind of a cheap reason because we could configure the truss such that there were no 0 force members, right? But I'll give you 2 quick answers and we'll talk about it in more detail. Number 1, we might need members there to serve as bracing elements. That's more of a steel design topic and we'll talk about that tomorrow. But 2, what if the loads move?
So it's a 0 load right now in a perfect scenario.
Okay. Yes, but we'll get to that a little bit more later. But the clickbait is, without doing any truss analysis, I could have told you that member DJ was 0 by just looking at the truss. And so what we're going to talk about next time is how do you look at a truss and identify the 0 force members. And we're going to look at a truss that's really weird on Monday, and we're going to probably be able to identify just by looking at it like half the members are 0 force members. And you'll find it's pretty slick. So that's all I've got. I'm going to pull up the code again, and I will see you all on Monday. You all have a wonderful weekend.